So in this video, we are looking at activity number 13. We're going to be graphing rational functions. You can see I've got a definition here for discontinuity. So go ahead and pause the video and take a moment to copy down that definition, and then we'll move on. So as I mentioned in the previous video, one of the important features of rational functions is that they have asymptotes, but we also sometimes have different types of discontinuity as described here. The thing that gives us discontinuity in a rational function is whenever the denominator is zero. You can see that's part of both of these examples here. What's different though is if we have a value of x that makes both the numerator and the denominator zero, then we're going to end up with just a hole in the graph. But if we have an x value that makes the denominator zero only and the numerator is some other value, then that's how we end up with a vertical asymptote. So with that in mind, let's look at this first rational function. We're going to sketch a graph, and I'm going to give you a little mnemonic device, kind of a structure to help us determine the important features of a rational graph and or the graph of a rational function, and then to be able to sketch that graph. So it starts with R, which stands for roots, or in other words, the x-intercepts. And this is going to have, the way that we're going to find the roots is that we're going to take the numerator and we're going to set it equal to zero. Because if it's an x-intercept, that means that the function value, the y value is zero. And if I have a fraction like this, the only time that this is going to equal zero is if the numerator equals zero. So, if I'm going to find out what makes it zero, one thing that's going to be easier for us is if we factor it. So I'm going to go ahead and factor the numerator, x plus 1 times x plus 1. So what we have there is x plus 1 squared. And if I set that to 0, well, the only thing that's going to make that 0 is x equals negative 1. So that's going to be our root, or our x-intercept. The next thing we're going to do is find the asymptote, specifically the vertical one, vertical asymptote. Vertical asymptote happens when the denominator is 0. So let's factor that denominator, x plus 3, x minus 3. And actually, we probably should have factored them both before we did this, because if we had either had a factor that was the same in the numerator and the denominator, they would divide out, simplifying our rational expression, and then that would also give us this hole that was described up here in the definition of discontinuity. But we don't have that in this example, so we're okay. I'm going to take the denominator, x plus 3, x minus 3, and set it equal to 0. That, of course, is going to be 0 whenever x is negative 3 and when x is 3. So we've got two vertical asymptotes for this rational function. Now, the next step here, it's a little bit, we're talking about some features of graphs that we don't always talk about. Tangency and togetherness. And this is kind of a weird word, possibly a made-up word, but it's a really good idea here that's going to help make the sketching of the graphs a lot easier. First, let's talk about tangency. And I'm writing it like this, kind of like a ratio, because tangency has to do with the numerator. If you have some factor squared in the numerator, then you have tangency. And what tangency means, and this is something that you hopefully saw in the previous activities when we were graphing polynomials, when you have a root like this where the factor is squared, we think of it as a double root. And what's going to happen on the graph is that instead of the graph crossing the axis here at negative 1, it's actually going to touch the axis and then turn back around. It's not going to cross it. It's going to make like a little parabola at the root because this factor is squared. So it's going to look parabolic there. So, and that's called tangency. We're touching the x-axis at that one point and then changing direction. All right. If we have a factor squared in the denominator, then you have togetherness. And what that means is that the graph is going to come together on either side of a vertical asymptote. The unbounded behavior on either side of the vertical asymptote is going to go in the same direction. So for example, I'm just going to do it around an asymptote. So if I have a vertical asymptote, it means that the behavior is going to come together. And they're either both going to be going to positive infinity, or they could both be going to negative infinity. Let me give you a little diagram of tangency also. If that's our x-intercept, tangency would look like this, or possibly opening up. The idea is that we're getting that parabolic behavior there at the x-intercept. So notice in this case, if I look at my numerator, I do have x plus 1 squared in the numerator. That's going to mean when I sketch the graph, we're going to have tangency. Whoops, I misspelled it. Tangency at x equals -1 at our root. There is no factor squared in the denominator, which is important because that means no togetherness. That means that whenever we have a vertical asymptote, the behavior on either side is going to be going in opposite directions. All right, next in our structure is E, which stands for end behavior. And hopefully we remember from the previous video that this is referring to the horizontal asymptote. Now, end behavior, remember that we want to know the y values approach what number as x approaches positive and negative infinity. So in this case, if x is going to infinity, here, my numerator and my denominator, these are both, if I just consider the expressions separately, they're both quadratic expressions. They're both going to approach infinity, and they're going to do so at roughly the same rate. And so what that means is that as we go to infinity, in essence, the growth here is going to cancel out, and we're going to be left with the coefficients on these numbers. Let's look back at the notes from the previous example, and I think we might see this a little bit better. Remember this function on example 1. If I look at my algebraic expressions, I have a linear expression on the top and a linear expression on the bottom. As x goes to infinity, these are going to grow roughly at the same rate. They're going to, in essence, cancel each other out, and what I'm going to be left with are these numbers here. Adding 3, think about this. If we're plugging in infinity for x, I can multiply times -2, so I have -2 times infinity. If I add 3, that's not going to make any difference to that number at all. -2 times infinity is so huge, the 3 doesn't matter anymore. This is infinity. If I add 3, it's not going to matter anymore. Really, all that we need to look at is the highest powered terms in the numerator and the denominator. Those are the ones that are really going to affect the behavior of the graph as x gets really large. And so if this becomes -2 times infinity over infinity, well, my infinities are going to divide out, and we're ending up with -2. Now, this is not exact math. Infinity is an idea, not a number. You can't really divide it out, but in essence, that's what happens. If we look at the second example that we did, again, if I just look at the highest powered terms in the numerator and the denominator, they're both linear expressions. They're going to grow at the same rate and in essence cancel each other out, and I would be left with 5/2, or that 2.5. So that's what's going to happen here. If I just focus on those x squared and x squared, just the highest power terms in the numerator and the denominator, they're going to grow at the same rate. They're in essence going to cancel each other out, and so my horizontal asymptote is going to be at y equals 1. And the last thing that we're going to do here is find our y-intercept. That means if we're going to find the y-intercept, I'm going to change all my x's to zeros, which would leave me with, if x is 0, then I'm going to have negative 1/9 for my y-intercept. So now with all of this information, we should be able to sketch a graph of this function. So let's see how that's going to work. I'm going to start out with the root. I've already put the root there at -1. I have vertical asymptotes at -3 and at +3. Remember that we're going to have tangency at our root. There is no togetherness. We'll talk about that in just a moment. Our end behavior, horizontal asymptote is y equals 1. Now remember, I like to draw that horizontal asymptote just on the ends of the graph because it's just about end behavior, not about what's going on in the middle of the graph. And then we have this y-intercept at -1/9. So just going to stick that in right there. Now, the important thing to remember about rational functions is that they always like to go toward the asymptotes. The asymptotes are kind of like a magnet that they're not going to be able to touch. So I can see here, I know that these two things are going to have to connect. These 2 points here are going to connect. And then the function is going to keep going toward that asymptote. Now here's where my tangency comes into play. Remember, we're going to have tangency at x equals -1, which means I'm going to make a little parabola. Because we had that factor squared, we had x plus 1 squared, it's going to make a little parabola. So it's going to approach that asymptote. Now here's where the other part of the t's comes into play. Since there were no factors squared in the denominator, that means no togetherness of behavior around the vertical asymptotes. And therefore, since this part of the function is going to -infinity, on the other side of that asymptote, the graph has to be going to +infinity. And then it's going to come down and approach that horizontal asymptote, working like a magnet, pulling the function close to it, but the function's not going to cross it out here at the end. Same idea over here on the left side. Since this function is decreasing without bound, on the other side of the asymptote, we need to increase without bound. And then this is also going to approach that horizontal asymptote. The end behavior is approaching 1. So the mnemonic device here, we call it RADI, and we're going to use it again on example number 2. So let's start with R, which stood for roots. Remember, to find the roots, I'm going to take the numerator and set it equal to 0. So my root or my x-intercept is at x equals 0. Next is the A for asymptote, and this is for the vertical asymptotes. I'm going to go ahead and factor my denominator. If I set my denominator equal to 0, we can see that we have vertical asymptotes at -4 and at 3. Next, we'll think about tangency or togetherness. I keep misspelling tangency, sorry. And if I go back and look at factored form, I don't have a squared factor in either the numerator or the denominator. So we're just going to say none. No tangency, no togetherness. It's important to acknowledge it because it's going to help us figure out what the graph should look like. E stands for end behavior. This is our horizontal asymptote. Now, in this case, if x goes to infinity, notice that in the numerator, I have a linear function. In the denominator, I have a quadratic function. As x goes to infinity, if I just focus on the highest power terms in both places, my denominator is going to be so much bigger than my numerator. Infinity squared is way bigger than 3 times infinity. And so what that means, if you think about fractions, as the denominator gets bigger and bigger and bigger, the fraction itself is going to get smaller and smaller and smaller. Let me say it again. As the denominator gets bigger and bigger and bigger, the fraction gets smaller and smaller and smaller. And so, in fact, what's going to happen on this one is x approaches infinity, y is going to approach 0. and that's going to be our horizontal asymptote. The ends of the graph, they're going to approach 0. Last thing we need is the y-intercept. That, of course, means we're going to plug in 0 for the x's. And if we do that, we get 0 over negative 12, which, of course, is just 0. All right, so let's put these things on our graph. My root, my x-intercept is 0, also happens to be my y-intercept, the origin. I've got an asymptote over here at negative 4, another vertical asymptote at 3, and then my end behavior is going to approach 0. So I'm just going to sketch that out here to remind me we're going to approach 0 for the horizontal asymptote. Now this is a little bit of a challenging graph here because we don't have a second point to help us out. Remember on that first example, we had an x-intercept and a y-intercept, which kind of helped us get the graph going. So I really need another point here. So let's just pick a number and plug it in. Let's say 1, if I plug in 1 here, I'm going to get 3 over 1 plus 1 is 2 minus 12 would be negative 10. So I get 3, negative 3/10. All right, so that's going to be roughly right here. So now I have 2 points. I know that these 2 points have to connect and that the graph is going to approach the asymptotes because that's what it always does. Now, back here at the root, remember, this time we do not have tangency. So we're not going to make that little parabola. It has to cross the axis here. It's going to cross, and once it crosses, it's going to go to that asymptote, which serves as a magnet, pulls it close. Next, remember there is no togetherness on this one. So if I look at my vertical asymptote at 3, on the left side, the function is decreasing without bound, which means on the right side, it's going to increase without bound. And then that piece, of course, is going to approach the horizontal asymptote at the ends. Over here at x equals negative 4, on the right side, we are increasing without bound. Since there's no togetherness, this is going to decrease without bound and also approach that horizontal asymptote. All right, let's do one more example here. I'm going to go ahead and just start out by factoring x minus 5, x plus 2, x minus 5, x plus 5. Whoa, look at this. We've got x minus 5 in the numerator and the denominator. This means that we're going to have a whole. So that's an added, before we even get to the root, we're going to have a whole at whatever makes both of those 0, which in this case would be positive 5. If I plug in 5, that's going to make my numerator 0 and my denominator 0. That means I'm going to have a whole. And in order to find the y-coordinate of the whole, which is kind of a weird thing to say, because how do you have a coordinate when you don't actually have a point? But we're going to locate the whole. If you plug in 5 to the simplified version of the rational function, we get 5 plus 2 over 5 plus 5, which is 7 over 10. And so that means that our whole is going to have the coordinates 5, 7/10. All right, let's do our radii. So for the root, we're only going to have a root from x plus 2 being equal to 0. So that's going to be at negative 2. My vertical asymptote is only going to happen at the remaining factor in the denominator. If x plus 5 equals 0, that happens at x equals negative 5. If we check tangency and togetherness, again, on this one, we have none. End behavior. So again, let's go up here and look. Most powerful term in the numerator and the denominator, they're the same. My numerator and denominator are going to grow the same. In essence, cancel each other out as x gets bigger and bigger and bigger. And so, again, we've got a horizontal asymptote at y equals 1. Those coefficients on those greatest power terms. And then the y-intercept, if I plug in 0 for all these x's, I'm going to be left with 2/5. So let's sketch this graph. I'm going to start with that hole at 1, 2, 3, 4, 5, 7/10. I'll say that's roughly right there. We have a root or an x-intercept at -2. We have an asymptote at -5. Vertical asymptote at -5. No tangency or togetherness. Horizontal asymptote at y equals 1. And then our y-intercept is at +2/5, roughly right here. Okay, so this time I have these 2 points, which is all you need to get going. We're going to connect those 2 points. It's also going to go to the hole and then continue on to approach that horizontal asymptote. And then, of course, over here on the other side, it's going to go and approach the vertical asymptote. Works like a magnet, pulls it in. Remember that we have no togetherness. And so since on the right side of this vertical asymptote, we are decreasing without bound, then on the left side, we need to increase without bound. And it will approach the horizontal asymptote. Okay, I know this is a long video, and I'm sorry, there's a lot to show you here. Last example, we're going to kind of turn it around and write an equation for these 2 graphs. And we're still going to use this radii to help us out. So first of all, let's think about the roots. Those are the x-intercepts, which of course are here and here. That's at x equals 4 and x equals -2. What that's going to mean for the function here is that if I plug in 4, my numerator is going to be 0. If I plug in -2, my numerator is going to be 0, which means the numerator, I'll just call this f of x, is going to be x minus 4 and x plus 2. At least part of the numerator is going to have those factors, because if I plug in these numbers, then that's going to make those 0. The vertical asymptote, from this graph, it's kind of hard to tell, but it is here at 3, at x equals 3. That's a vertical asymptote, which means that my denominator is going to equal 0 when x is 3. So that means I'm going to have x minus 3 in the denominator, because if I plug in 3 there, that makes that 0. Now, tangency, if I look at my roots, I'm crossing the axis at both of those, so we don't have that. But togetherness, look at this. We've got both sides here are decreasing without bound around this asymptote. And that means that this x minus 3 has to be squared. It's the first time we've seen that in these examples, that factor in the denominator is squared because the behavior is going in the same direction. All right, end behavior here. It looks like we're approaching 2 on this side. It's heading up to 2, and on this side, we're coming down towards y equals 2. So let's think about what that's going to do to our equation here. Notice in the numerator, if I multiplied this out, I've got an x times x, so it would be x squared. And in the denominator, I have an x squared. So both parts of the rational function here, they're growing at the same rate. They're both quadratics. They're going to grow together. And so when they undo each other, I want to be left with 2. That means I'm going to just multiply the numerator by 2. So if I multiplied this out, I would have 2x squared on the top and x squared on the bottom. That would give me a horizontal asymptote of y equals 2. And then my y-intercept is here at -2. Let's check the math out here. Actually, I think it's a little bit above that. I don't know that it's right on it. Let's see what we have here. -4 times 2 would be -8 times 2 is -16 over 9, which would be a little less than -2. And I think that looks like where we are. Y-intercept is -16 over 9 for what we have here in our function, which just means it works. It's kind of hard to be exact about that, but the function we have here is a possible equation for this rational function. One more. We've got a root at x equals -2, which means for our function, my numerator is going to be x plus 2, because if I plug in -2, it's going to make that 0. And this is the only root. Asymptotes, right here at x equals 1 and at x equals -3. So that means those values of x make my denominator 0, x minus 1, x plus 3. Tangency and togetherness. Notice if I look at my root, we've got that little parabola shape happening there at the root. It's not crossing, it's turning around. That means that my factor in the numerator is squared. Remember, tangency is the one in the numerator. For togetherness, if I look around my asymptotes, I'm going in opposite directions around 1, opposite directions around -3. So neither of these should be squared. End behavior, again, it certainly looks like we're approaching 2. So a horizontal asymptote or in behavior approaching 2, which means, again, I'm going to multiply by 2 in the numerator. And so that gives me, and we could double check, we'll double check the y-intercept and see if what we have makes sense. If I put in 0 for my x's, what do we get? 4 times 2 is 8 over -3, -8/3, which certainly makes sense. -2 and 2/3, that could certainly be the coordinate for that point. So this equation here makes sense for this graph. Again, I apologize for the long video, but there was a lot to cover there.